YouTube and Twitch. So in our last episode, I kind of started implementing a bit of friction handling. I've disabled it for now. The only thing that changed off stream was this part of the friction code. Uh, um, the reason why I disabled the friction code is because we have sort of artifacts in our simulation. Um, yeah, so I was like, what is up with this system? It's not working properly. Um, and um, I think the penetration resolution is fine, uh, at least mostly, but as you can see, whoops, I have something in the background, as you might see from the console, that needs disabling. But you can see that the objects are not interpenetrating, as at least from what I can see. It seems like the position solver is doing things properly, but yeah, it's kind of hard to debug what we're actually doing when the OBB isn't represented by actual lines and but just this diagonal, and I have no way of seeing the actual contact points for the collisions and the contact normals. So therefore, I would like to implement some debugging visuals instead and remove this kind of diagonal line and instead have a box around the object that rotates or rather represents how it's bounded in space. Um, I also want to be able to draw dots or at least some basic squares for each contact point and draw a line, a short line for representing the contact normal. In general, I would like to be able to draw things so that debugging gets way easier. It will be much easier to see what's going wrong whenever we can see what's actually going wrong, going on. So yeah, that's what I'll be spending time on today. Maybe we do get around to uh, creating some fixes for the physics system. I don't think we need eight iterations of the penetration resolution method, but yeah. But that's the whole goal of this part of this stream. So let's kind of create an outline of what we want. Sorry for the flash. Let's see, let's do black for the background. So we kind of want to do some OBB drawing. We want some decalls slash points. I call them, or we could call them billboards for representing points. And we want some line drawing. Which we already have, so, and we could kind of collapse this into something like a um, uh, contact manifold debugger. This is going to use our line drawing system. I think this is it. So I think we will start by drawing the OBB because generally we have already most of the code that needs to uh, draw, that is needed to draw an OBB. This is some kind of package where I'm unsure whether there should be some time restriction or maybe it should just be a buffer that gets zeroed out because we want this for each frame, but we want to allow several contact manifolds. Yeah, the OBBs should just be a system where we kind of upload the OBB and just draw it. We want to create space for it at initialization time. For instance, create the relevant buffer space. So right now we build some debug information. We do it. Okay. Yeah, we need to do some uh, memory management for that. Okay. So we can add a box. Right now we don't remove anything because it's not needed. Objects don't get destroyed. We can change the color of a box without changing the vertices. We can't remove it. That is for the coordinate system. So yeah, we kinda do it automatically for our lights. And we make sure the rays are put in the okay, maybe I want to restructure all of this. Maybe we want something that is drawn for a single frame. Although we don't have any way to pause anything. Do not have iterative stepping between frames. Uh, Even though we could implement that. Yeah. So this is not actually a good name for it. Hmm. Maybe we want a separate buffer for contact manifolds. And maybe we just want to use our existing system for the OBB and random race. I mean, the contact manifold is going to be up to several instances of 4 points, preferably 4 points, 0 to 4 points, and 1 to 4 points to be exact, and a single contact normal represented by 2 points. Uh, hmm. Yeah, maybe we just want to separate it like that. I would like a more generalized system, but generalization I think is probably subject to change and might get complicated to solve before we know our long-term needs. So yeah, we asked the renderer to create space in our buffer for our static bounding boxes, dynamic bounding boxes, dynamic bounding spheres, which, oh, okay, yeah. We also want a representation of bounding spheres that are more uh, still in the line drawing system. But yeah, we want to add that as well. Okay, so this is not build debug information. I should rename this build debug information. Create bounding volume buffers. That is what it's actually supposed to be called, because that's what we're doing. And next we add the bounding boxes. We're not using this anymore. All right. We could do a generalized method where we could do an enum. We could do an enum. But it will only be, yeah, we will only have two kinds of boxes. And we want a constant integer of type. Type 0 ABB. Type 1 OBB. Yeah, because we simply and then rename that to ABB. And this is fine because it's going to be a generalized method. uh, let's see. Then we do a type const int. Let's do unsigned int type. Oh, no, I didn't. Const unsigned int type. There we go. If type equal to 0, do like this. Else if type equal to 1, we do something else. Yeah, well, maybe we should change this because inside our game object data, our OBB has some information here. We could simply pass in the pointer to the axis if we wanted to. So we could do something like a vector pointer axis, which will be set to a null pointer. And we have all our default values here. So we can set the axis. I'm not sure it really matters that much. We just want to be able to use the same function to create an OBB instead of an AABB. I'm not sure it matters too much. Then we simply check if we have any access. We can do this. This is all done at initialization time, so during runtime everything should be set. Let's comment that out for now. So if we pass in some axes, now we have the center position, the half widths. We can keep on doing that in terms of floats instead of the register. Yeah. Do I have a math method for loading 3x3 floats into, or rather store float? The float and then store float 4x4. So we could take a matrix. Yeah, the problem is we would need some sort of clipping, or rather maybe just permutation. We could do some version here where we it's not that I mind too much having a register here. It was just more for okay. Let's do a gflow 3x3 and just implement the method real quick. Do we want it passed by reference? No, let's do a pointer. Okay. Well, how should I do this? I don't think it matters too much. No, let's just do the register reference. Yeah, let's not bother with that for now. Yes. So we pass that in and we do some, let's close a lot of this since we don't need it right now. In here we have a problem because this is just going to take an update. The sphere doesn't change, but we would like to refine it. So that we might end up with an actual sphere-like bounding volume. Anyway, so for now, everything should be working as it were. Let's see, not yet. Do we have an error anywhere? I can't seem to find it just by looking over the thingy here. Okay, I have to. For some reason, I do not get the error output. Warning, 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 warning. Warning. Failed. Error. Okay, I copied in some default arguments. Oh yeah. It was staring me right in the face, but I didn't register. Okay. Um, so inside our SAT, I think it is, we actually do have a method that calculates the bounding volume of an OBB. I think this is exactly it. We're going to steal that and go into our render utils and create a method. Where we create a vertex line. Build OBB vertices. And we do something like let's see. G vector, DC vector, pointer axis, and then const float pointer path widths, and then what do we pass in? Okay, let's basically copy this. And then add a G vector pointer axis. There we go. Let's see, we simply reduce this to axis. And then we have radius. And then we do G vector center, where we math load float 3. We load the position. reference, and we simply calculate the vertices here. So I think this would work. We calculate the points then for our 8 points. We build some vertices. Return vector. And let's do a vertex line temp and say the position, which is a defloat free, where we simply math store float free. Let's see. Temp pos, and then points I. We simply store the position, and we say the color is equal to, is it a float for, yeah, to the color. Is that it? It might be. Okay. We simply build the indices kind of traditionally. Let's see. Of course, we want yeah, right now we do not support padding. Which is probably fine. We will just draw the box as it is. Half width and the axis. There we go. We calculate the different information here. Exactly the same way. And then we increase the offset. All right. I think that is the way the initialization of the box is supposed to be handled. Now we can actually spawn it with let's see, bounding boxes. Oh, it's in the box axis and pass that by reference. Isn't it? Let's see. Okay, we can take that as a const pointer. Doesn't really matter. What? Yeah, I figured so. Let's see, and we change this to a const. There we go. Yeah, it's already an array. Does this work? It might. Oh well. Before let's see. We don't need to scroll through that every time. Okay, and we of course want the yeah, we kind of changed the offset here. So the dynamic spheres, yeah, we need to add one more, I think, by changing the update visual color only. Huh. Maybe it's down here. Yeah, I think so. Plus M size. Yeah, I think we're supposed to. Yeah. So it starts with that position, but it's not updated. This is color based. We actually do not use that for now. Then we want to use the dynamic bounding volume and actually update it inside our renderer. We might want a update visual. Whoops. Okay. OBB. We could do a G vector half width. Hey, G vector pointer colors, or rather axis. Maybe. Nah, we need the. We can't set it to a null pointer. Maybe we just want to keep it as floats. Yeah, we're basically gonna mirror a lot of the stuff here, but we're gonna use the version where we build the box like that. Let's see. So let's see. Let's do this for all our things here, and let's do update OBB. I think, wait a minute. First we get the position, meaning the center, not this. Okay, we have to change these things a bit. Do we have some old code? Update visual box. We simply pass in the information here. The centers, parts of the float constructor. Okay, we can do that again. Okay, so we do the offsets, then we do the constructor for the float free. And then like that. And then we do okay. Well, this is because we're doing the half widths constructor here. Whoops. Let's see. Oh, wait a minute. We do like this and then like this. And then we do not the color, but the axis and then the color. And let's just leave out the padding here. Too many initializer values. Huh? First we take the offset, then we take the position, which has these three components. Did I just copy in too much stuff? No. Then we have position. too many initializer values? I don't think so. Did I miss a comma somewhere? It doesn't like when I create the array like that, I think. So let's do const float half widths, an array of 3. Let's do like that, and then pass in the half widths instead. All right. Let's step through the code and see what crashes us. Let's see. Maybe we simply want box, 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 box. So that is fine. Okay, we get an exception in there. So the box vertices, what is the offset? 6. Box vertices 0. That's not great. Okay. That's not great. We might have a problem somewhere. And then, do we have our points? I think so. Oh, I do. I forgot to place the, or rather the temp here. And that's why nothing's happening. Let's see. Yeah, now everything works fine without any. Okay. The box is drawn weirdly, but we do have a box. It's really, really drawn weirdly, and I think it's because of the way we calculate the indices. Yeah. I think we need to arrange this method so that the points are arranged the same way as our standard AABB method. So I'll just copy this and use it to rearrange our points. So we want this order of the vertices. Yeah. just gonna reduce the spacing so it'll get a bit easier to read down here. So let's arrange these points in this order. So first one is going to be the pluses, that is fine. Second one is going to be the minus and then the plus plus, which is actually this one. So let's move that, call that one. Then the second one is supposed to be the minus plus minus, which is this one. And then the next one is going to be the plus plus minus, which is this one. 3. And then plus plus minus, then plus minus plus. That is actually that one. Great stuff. And then we have minus minus plus, which is this one. And we have minus minus minus, which is that one. And then we have this one, I think. Yeah. So now the order is the same, which means the indices correspond to the correct corners. And as you can see, the bounding volume is now drawn correctly. But we already see an error, which is great, which might explain why our velocity, our physics engine is not resolving this correctly. As you can see, the bounding volume does get reoriented, but the model actually shows things differently. This is why debugging is so absolutely mandatory to implement. Okay, so that for that part of the rotation, it gets yeah. So the bounding volume is actually the one that is handling the collision, and the mesh is just drawn from the object transform matrix. The renderer just takes that. So this means that somewhere in our code, we do end up with an incorrect bounding volume, which might explain some of the weird behaviors we've been seeing in the physics solver. Now that is absolutely great. At least that we now can debug it. Okay. We can then, in our application here, simply remove the step where we kind of draw the yeah, the diagonal. We don't need that anymore. Let's see, let's just comment this out. Okay, that is so awesome. I didn't know that the bounding volume actually ended up being incorrect. It's kind of like opposite in terms of the actual rotation. Yeah. Okay. So somewhere Now the diagonal is gone, and we're back to our old shooting race. Yeah, as you can see, everything simply turns in the opposite direction. Huh. Since the same code is used for grabbing the vertices, which are part of our contact manifold, this means that our contact generation is not correct. Yeah, I have to figure out where the bug is introduced. Yeah, the bug might be introduced in the hmm. Is it this part of the algorithm that is wrong? I mean, this worked before when I drew the diagonal. Maybe I need to transform the bounding volume data in world space coordinates. Uh, Everything is simply kinda inverted. I wonder if I change the utility method here and I simply just invert everything. Let's just try that. Oh, well, that doesn't work. It flips the whole thing. I mean, this is also how the physics engine cookbook guide does it in terms of calculating the vertices of the box. So we update the matrix. It's almost like one of the axes are flipped. I mean, then it gets Let's try normalizing this. Probably doesn't do anything. No. If I flip one of them, vector negate. Not that one. Maybe the y-axis? No, probably not. Maybe we want to actually do what we usually do. Maybe we want to um, instead of copying it, maybe we want to apply the rotation by doing the inverse. Yeah, maybe we want to do that to change the basis of the vectors here. So for instance, we do the whole thing up here. So we do a rotational matrix. Match matrix axis. And we simply set every axis. And the last one as a 0 vector. We still set our position. We then set we set axis to the math times the axis times the math transpose of the math, and then set these 3 to the axis vectors. I think I might not be applying the rotation correctly in the old method. It was a problem before, but yeah. Let's try this. Whoops. Okay, we have a crash. Let's step through that. Okay, let's see, where do we have the crash? Okay. There's no crash here. When how do we get the crash then? Because okay, it's when it's rotating over. Okay. So now the bounding volume is not rotating. What if we just do like this? We probably end up with something over rotating. Yeah, that's not great either. So is the problem inside our actual debugging? Because I mean, if I could just get it to rotate. Do we have a collision in terms of the bounding volume? Yeah, it seems like it actually listens to the bounding volume and not the actual object. I mean, you can see the bounding volume isn't allowed to penetrate anywhere. Almost anywhere is perhaps an exaggeration, but it's like the bounding volume is the one that is actually ending up uh, being handled in the physics system. So maybe we need to change how the orientation is calculated, because right now it's kind of inverse. Our bounding volume is behaving the way it kind of should, at least in the terms of the physics simulation. But the visual representation of the object is not correct. So inside here, we calculate from the orientation, which is the quaternion, and maybe it's during our integration step here. Maybe if I scale this negatively, let's see. No, it doesn't solve it. And this should be not important which way I multiply the quaternions. Let's see. Yeah. Somewhere, somehow. I mean, now the physics simulation kind of makes sense since it's using that bounding volume to detect collisions. It's clipping the contact points by using the bounding volume. It's simply not orienting the it's not orienting the object correctly. And it's not because I introduced an error in our debugging part of the update here, right? Half widths. The way. Yeah, so either the way the center I would simply like for the bounding volume to follow the orientation of. So yeah, if you simply transform the half widths, which are in object space by the world transform matrix, you end up with the correct result. I think the way I perhaps calculate the bounding volume vertices is the one that might be incorrect. Kind of want to flip it. But where do we want to negate this one? And this one, perhaps? It doesn't really change anything, it seems. I mean, this method is supposed to change the visuals. So the axes are not important. If I change this, if I just change these, I don't end up with anything weird. Am I not using the correct one? I mean, I do. Probably doesn't matter because it's kind of flipped. Okay. Maybe I just want to flip some of these points. Okay. If we kind of log that out, maybe by the order I do it, I end up inverting stuff. So this is going to be subtract, this is going to be add. This is going to be add, 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 and then subtract. Let's try that. Whoops, I don't want to change that. Yeah, that definitely doesn't work. So we could try doing this one and then see if, yeah. Well, of course we have to flip that as well. So if I add and then subtract, and if I subtract, then add, and if I add, then subtract, and if I add, then subtract here, and if I don't think this is going to work from the looks of it, and then subtract. correct, and then add. This doesn't flip anything. It mostly just looks weird. And the physics is kind of using the bounding volume we're seeing, of course. But I mean, if I can get the visual representation to look like the object. Let me try. Negating some parts. We only do the just for the lols. No. I mean, it's like it needs to be mirrored over the diagonal, right? I mean, the diagonal might be from down there up to the corner. If it were flipped around the diagonal. If I change the order here, it will probably not do anything, but whoops. There we go. No. I mean, like, it's like it's supposed to be rotated 90 degrees, or perhaps not 90 degrees, maybe 90 degrees on several axes. Let's do something where we, if I is equal to 1, then we know it's the all negative. Then it's, if it's equal to 7, we know it's the all positive, meaning that this is the minimum, and this is the maximum, and then we will do the color for whatever. But we want to set the color to, yeah, let's just do red. And then green for this. So yeah, the maximum is there, the minimum is there. Yeah, so the C component of the maximum needs to be flipped. Obviously, because it's seemingly negative around the center of the object, and the object in space is pointing in the positive direction. Let's try math negate here. Does that change? Not the way that we expected, at least. No. So flipping the C is not that it. Maybe we want to change the Y. No. Let's try something just for fun. Negating the center. It's going to be totally whack. Yeah. Hmm. Hmm. Okay. Okay, okay. Let me see. So where was I? Hmm. Let me just check out the algorithm I have. Manifold construction here. So axis 1 times the edge 1 plus And I have to be sure that I already checked, but I'm gonna double check. So the half widths I put in like that. The axis I put in like that. I mean, even the minimum and maximums are not correct. Nothing about this is correct. When I create the object, down here, bounding volumes, sphere, bounding boxes, OBB, what if I flip that one? Well, it gets recomputed, computed. Oh, let's see, maybe it's due to maybe the bases are not getting fetched correctly. Maybe we're accidentally inverting everything by not transposing the matrix correctly. Let's try that. G matrix test equals this one, math. Transpose. And let's copy this, comment it out. Whoops. And then simply do like this, because that might be why we're getting something that is inverted. Yeah, that is it. It was the memory ordering. That is why the whole coordinate system simply just got flipped. Every axis got flipped. That is great. All right. I'm starting to get the hang of all this math stuff. All right. Everything seems to be working. And since we pass in the OBB, the physics system also does everything kind of like it's supposed to. Great stuff, great stuff. Now that was that era. let's see how everything kind of behaves after we've started building the axis of the the OBB correctly. Yeah. Let's try adding the velocity solver. Probably won't have changed a lot, but we're still having the weird sliding for some reason. I mean, if we disable the friction-based part of the computation here, we end up with our old frictionless system. For some reason, this is kind of okay. I guess the bounding volume is sliding. The movement of the object makes a lot more sense to me now, once I can visualize it. Yeah, you can see the contact point there, kind of pushing it off, but I guess the contact point did kind of slam into the ground of sorts. Yeah, anyway, we definitely need to do some contact point drawing, but this is a great first step. We basically did the part where we do our OBB drawing, which is really great. Let's see. Maybe we just want white lines. And then let's try not to do that. The system behaves more like I'd expect. It still has some quirks, but now you can at least see what's going on. Sleep number 2. I do it not there, but up here. Okay, the physics is not where we want to close. New physics. We do white lines, and then the minimum and maximum is represented by the green and red corners. Okay. Maybe the dampening is way too high. Let's see. That's our OBB thingies. Let's do maybe some less dampening here in general. Then the friction just picks up. And it starts doing silly stuff. But at least now we can see that our bounding volume is doing what it's supposed to be doing. Let's make our algorithm use the actual friction stuff here. Yeah. It's definitely kind of exaggerating a bit. That force there doesn't make any sense. Any sense at all. It's kind of living its own life. Whoops, 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 whoops. Let's see, when I calculate the inertia tensors, is it that? Okay, maybe I need to transpose this as in the previous function. I mean, it kind of stabilizes in terms of the wiggling. but it just keeps sliding forever. It just keeps on sliding forever. Forever sliding. And that's not what we want. Anyway, I think we've gotten to a point where we would like to be able to draw some contact manifolds, since we got that sorted. Hmm. Yeah. Yeah, so the thing we figured out is instead of calculating the bounding volumes by simply taking whatever is in the matrix, which is column uh, major ordered, which I don't think the way our axes are built is in line with that. Um, we simply have to invert it. Also, this, or perhaps it's just because we would like the inverse matrix to get it in object space. Yeah, yeah, that is it. That is why we do the transpose, because when we only select out the 3 by 3 matrix, and when we transpose it, we actually get the inverse of the rotation matrix. Which is the local axis coordinate space, I think. At least it works, but I think that's the way we're supposed to understand it. Let's see. Okay. I still want the slam function inside our application for debugging here. 10 iterations. Yeah, it really just does some stupid stuff. We don't want to add torque, but we would like to be able to slam the object into the wall. And then it falls over. And kind of, yeah, it doesn't seem extremely stupid the way it works. It's still kind of quirky. And we definitely want um, some adjustments to it, and I want to figure out why on earth everything is so buggy. I think it's something to related to our matrices. I simply think that we are storing perhaps some matrices wrong. Let's disable this for now, because with strictly frictionless based handling, yeah. Yeah, I'll implement the contact manifold debugging stuff after a break. I'll grab some food and yeah, do a bit of thinking. As per the YouTube series, I'll be rounding this one off. We're done with this. And we will probably just do this since the last one is more of a convenience since we only have one bounding sphere and it's related to the future. I also need to find an algorithm that can uh, vertex sphere simplification, create vertices simple maybe. Okay, we can look into that. Generating meshes. The UV sphere or the icosphere. The quartz sphere. Okay, easiest. Yeah, seems like I have to do a bit more work. Lines. Yeah, I think. Yeah, that's kind of elaborate. Um, yeah. Okay. I'll definitely create sphere like line segments vertices. Okay, maybe I just create a model. Uh, Tessellation, create sphere. Point. How do you programmatically? Hmm. All right, there are some different suggestions here. It looks like a lot of work, so that will definitely be for another part of this streaming series. Anyway, I think this is a great point to end this YouTube video. Um, yeah, in the next one I'll be adding some debugging for the contact manifolds, just so that I'm able to draw them. Yeah. But hopefully I'll be seeing you around. If you found it helpful, comment, like, or subscribe. And remember, kids, always do your math homework. It seems to be paying off at a later stage. Bye bye.